So we spent our time in the last topic of the course looking just at how the operations of multiplication, division, and exponents interact with one another. Looking at solving problems that involved simplifying expressions in which the only arithmetic that was going on was multiplication, 3 times u to the third times v, division, and exponents. Here, a power, another power. We're raising powers to powers. We're using distributive properties, and so on and so on. And what we did last time is we developed this whole catalog of properties that we can use to simplify these kinds of expressions. And these expressions are what we call monomial expressions. We call them monomial because we only had to worry about multiplication, division, exponents. What we didn't have to do was we didn't have any addition or subtraction on the table. And so that gives us one term. And when I say term, terms are things which are added or subtracted to one another. So all of the expressions we worked with in the previous topics were just single term expressions. There was no plussing, there was no minusing, except in the exponents, which doesn't count. And so these were all what we call monomials. Mono for one, nomial for name, one term, basically. Of course, that leads us into the next topic, which is what do we do if we want to work with expressions that also involve addition and subtraction? What if we have more than one term to deal with? How does that change the way that we apply exponent properties, or the context in which we apply exponent properties? How do we build new methods for simplifying expressions, and then ultimately new methods for solving equations, which is, after all, the other side of algebra, besides simplifying, is solving. How do we build new methods for solving equations around the idea that we might be working with polynomial expressions, expressions with multiple terms that involve multiplication, division, and exponents? So that's the next bridge for us to cross, and really, that is the remainder of our semester. It's spent looking at polynomials and all the different ways that we can simplify them and solve equations involving them. That is what we will do for the next many weeks leading us to the end of the semester. We can really push polynomial algebra really far. We can push it all the way up through the upper echelons of the math major and into current research around mathematics. There's a lot that we don't know about polynomials. There's a lot that's almost unknowable about polynomials. For example, we know that we can solve any polynomial equation if the highest exponent is 2. We're going to develop techniques in this class to solve any polynomial equation whose highest exponent is 2. That's great. Mathematicians also know that we can do a similar process for degree 3, degree 4. But degree 5 is a different story. We can't actually solve just any polynomial equation of degree 5 through the same process that we use for degrees 2, 3, and 4. That something runs out. There's this property that runs out when we get to degree 5 that means we can't necessarily always solve them in the nice way that we do with 2, 3, and 4. So there are a lot of very long stories that begin with the polynomial algebra that we're going to look at this semester. So we also could get really fancy and look at polynomials that have several different variables in them, like the monomial that we saw a few moments ago. Right? These monomials that we worked with on our last class, generally just to get us the practice in applying all these properties, we looked at monomials with several different variables, a u, v, and a w in this example, an x, y, and a z in this example. But when we make the pivot to polynomials, for us, we're mostly going to restrict our attention to monomials in a single variable. So we're not going to have x's and y's running around for the most part. We're going to restrict our attention to just polynomials in a single variable. So an example of a polynomial expression might be something like 5x to the power 6 minus 12x to the power 2 plus, I don't know, 1/6 times x minus 10. Okay. So this is a polynomial expression. Each of the single terms could be called a monomial. And when I add or subtract them all together, I get something which collectively is called a polynomial. So my first question is, how many terms are there in this expression? This expression has 4 monomial terms in it. And again, each of the monomials we recognize as just being something which is made up of only multiplication or division and exponents. So here are my 4 monomials, and the subtractions and additions divide up this polynomial into its 4 monomial parts. Right? So here are my 4 terms. Each one of the terms I can also break apart into 2 pieces. So just to get some terminology on the table. This first term, 5x to the 6th. I can break that apart into two pieces, what we call factors. So when I use the word terms, terms means that we're adding or subtracting something together. When I use the word factor, what I mean is that things are being multiplied or divided together. Multiplied or divided. And so this first term, 5x to the 6th, I'm going to think of as being comprised of two different factors. One of those factors is a constant, the number 5. Anytime there's a constant factor in a monomial, and there always is, even if we don't write it, we're going to call that factor the coefficient. So when I use the word coefficient, that's always what I mean. This is the constant factor. It's the factor that doesn't have a variable in it. Right? Etymologically, we call it the coefficient because once upon a time, a couple hundred years ago, this is ancient terminology, once upon a time variables didn't used to be called variables in algebra. They actually used to be called efficients. Efficients, as in they can do something. Variables are there to serve a purpose, to effect change. And so variables used to be called efficients in our great-great-grandparents' time. And so coefficient then became the thing that is not a variable factor that rides along with the efficient. So you'd have a coefficient and you'd have an efficient. We don't use that language anymore, so I tend to just call this part the variable factor. But we could call it the efficient if we wanted to. So every monomial has a coefficient attached to it, and it has a variable factor. And the last piece of terminology that I want to get on the table is that we also want to give a specific name to the exponent, which is a part of that variable factor. So the number 6 here, as an example, we're going to call that number, instead of calling it the exponent, we give it an even fancier name. We call it the degree of this monomial. So those are kind of the three pieces that are most important in looking at any one term of a polynomial. What is its coefficient, the constant factor? What is the variable factor, that factor which is not the coefficient? And then what is the degree, the exponent which sits on that variable? And because all of our polynomials for our purposes are going to be one variable polynomials, there won't be a question of, oh, which variable factor do I look at for the degree? We're just going to look, there's only going to be one exponent in any given term. And so that exponent is what we call the degree of this monomial. So real quickly, what is the coefficient of this second term?
12x.
Careful. A different answer over here. It's customary, so the coefficient is always the constant factor. So the coefficient itself will never have an x in it, it'll just be a number. And the other thing that we often do with the coefficients is if I have a monomial which is being subtracted, I'll take that subtraction sign and make that a part of the coefficient as well. In other words, revisit this subtraction and think of it as addition of the opposite. Keep, change, flip, right? And looked at that way, what would we say the coefficient of this factor is? Negative 12. So there will be our coefficient. I'll just abbreviate it, coef. And then what's the degree of this monomial? It's 2. So the degree of this monomial is 2. Okay, great. Third term, this one right here. What's the coefficient? 1/6. And what's the degree? How many powers of x are here? It's either 0 or it's 1. Let's try and suss out which one it is. What does it mean, and we talked a little bit about this last week, what does it mean to have 0 powers of something? If I take x and I raise it to the 0 power, what's that the same as? It's the same as 1. It's the same as not having any x's whatsoever, right? Whereas if I raise x to the first power, what are we saying that that is? That's just plain x. Right? So an undecorated x, like this one, is the same as having an x with an exponent of 1. A missing x altogether, that's where we get an exponent of 0. So for this term, 1/6 x, what would we say is the degree? 1. There's that little secret 1 up here. That's the coefficient of this term. All right, and then what's the degree of this last term? First of all, what's the coefficient? Negative 10, bringing that negative sign along to correlate with the subtraction. And then what's the degree of this last term? There are no x's in it at all, so the degree is no x's at all means the degree is 0. If the degree were 1, there would be an x sitting in that term, because x to the first power is x. But x to the 0 power, that's no x's at all, right? And then this last term has no x's in it at all, so the degree of that last monomial is 0.
Does that only work with variables?
So the last thing that I want to do before we move off of this sort of scene setter, we looked now at each of the terms in this polynomial separately and said, here's the coefficient, here's the degree, here's the coefficient and the degree, coefficient, degree, coefficient, degree. The last thing I want to do is for us to look at the polynomial all together, because we don't want to always have to parse the pieces of this individually. And the most important definition for us is, what is the degree of the whole polynomial? Does anybody remember how to do this? Not the degree of an individual term, but what's the degree of the whole thing? Where do we find it? Again, this is nothing more than a definition, at least for now. There's no real arithmetic for us to do. It's not really a deep thing yet. Because we have sort of 4 different degrees to choose from, 6, 2, 1, and 0. And among that list, we want one of them to be the degree of the whole polynomial. Which one do you think we choose? The 6. Why? Yeah. So for reasons that are right now beyond our ability to explain, right now as in this point in the semester, maybe in a little while we'll see why, the degree of the whole polynomial will be the highest degree of any of its monomials. So in this example, that degree is 6. And so just to gild the lily with some additional terminology, what we do when we talk about the degree of an entire polynomial is we single out that whole term that has that highest exponent, so the 5x to the 6th term in this example, and we will call this the leading term. It's the term that has the variable factor with the highest exponent, the term that has the highest degree among all the monomials in this expression. And for that reason, we'll also call the coefficient of that term the leading coefficient. These are all these are all words that I'm likely to use as we get deeper into polynomial algebra. So I want to make sure that we get on the table now what I mean when I'm talking about these ideas. Right? So for an entire polynomial, the degree is the degree of the highest degree among all of its monomials. So in this example, that degree is 6. And that degree lives in the term that we call the leading term. It's the term that has the highest exponent, and the coefficient of that term is called the leading coefficient.